Hey everybody, welcome back. So today we want to talk about evaluating a triple integral using cylindrical coordinates. So let's take a look. We have the following. So for our outer integral, looks like we're going from -3 to 3. For the middle integral, looks like we're going from 0 to the square root of 9 minus x squared. And then for our inner integral, looks like we're going from 0 to 9 minus x squared minus y squared. And inside, so for our integrand, we have the square root of x squared plus y squared. And the order, this will be dz, now dy, and then dx. Okay, so the first thing I want to do is think about what's happening in terms of z. So we want to note the following. We want to note that z goes from 0. Well, z equals 0 is the xy plane in R3. Sometimes I refer to that as the floor, but z goes from z equals 0 to z equals 9 minus x squared minus y squared. And so this is an upside down paraboloid, right? So this is sort of the classic elliptic paraboloid with its vertex at the origin, but upside down or reflected, and then translated up 9 units. A good way to think about what's happening here is that in some sense, this will edit how much of this we consider. And let's dive into that a little bit further. Now, y goes from 0 to the square root of 9 minus x squared. And lastly, x goes from -3 to 3. Okay, so we know what's happening on z with z, right? We're going from the floor to this paraboloid. And then let's see how we're going to, in a sense, edit that further, how much of this we consider. So in the xy plane, y goes from 0, well, y equals 0 is the x-axis, to y equals the square root of 9 minus x squared. Well, we know y equals the square root of 9 minus x squared. That's the top half, right, of a circle of radius 3 centered at the origin. So I know I've got the top half of a circle of radius 3 centered at the origin, and then this will tell me how much of that I consider. So each of these sort of edits the previous further and further. So since x goes from -3 to 3, it looks like I'll consider this entire half circle here. Now, since this region is circular, and also we know that x squared plus y squared is r squared in cylindrical, those are big hints to use cylindrical coordinates. So how do I talk about this region in cylindrical coordinates? So the next goal is to describe this. So let's say that. So next goal. So describe in cylindrical coordinates. Okay, well, that's just fine. So let's recall some facts about cylindrical coordinates. So we know that x is equal to r cosine of theta, y is equal to r sine of theta. We know that z is equal to z. And what else do we know? Well, we know that the volume element is equal to r dr d theta dz. And we can permute these as long as we're careful and write this as r dz dr d theta, etc. I think we'll end up using this version. And what else do we know in cylindrical coordinates? Well, by the Pythagorean theorem, we know that x squared plus y squared is equal to r squared. So that's pretty handy. Okay, so let's deal with z. So our goal is to describe this using nothing but r's, thetas, and z's. Now 0 is constant, so that's not going to change. But one thing I want you to notice right here is if I were to factor out a minus sign, that's the same thing as this, right? So just by factoring out a -1 or a minus sign, that's the same thing as this. Well, here I've got exactly 9 minus, well, r squared, right, in cylindrical coordinates. So I can write that as 9 minus r squared. That seems nice. Okay, so let's talk about r. So r is the distance to the origin. So we pick up all distances from 0 to a max distance of 3 units away. So r will collect all distances from the origin of 0 to 3. And theta, that's measured from the positive x-axis or the positive polar axis. So theta goes from 0 to pi. And that seems pretty nice. Okay, so I think I'd much rather deal with this than this, right? So this seems promising already. So let's go ahead and take this information and rewrite this. Don't forget, in cylindrical coordinates, we're going to call this r squared, right? So this will be the square root of r squared, but since r is non-negative, right, that'll just be r. And then just remember that this is dv, which we can rewrite this, right? We call this our volume element. Okay, so what are we looking at? So I think just for the sake of completeness, it would be nice to write that this is equal to the new version with a change of variables to cylindrical. So I am going to rewrite this. I think that would be a very nice way to present our work. Okay, so that seems nice. And that was, we said dz, dy, dx. And let's take a look again. Okay, so our z integral is going to go from here to here. That'll be the inside integral. Now this will be the r integral. R is going to go from 0 to 3, much nicer. This will be the theta integral, which goes from 0 to pi. So I'm going to do this inside out. I call that reverse onion style. Right, so reverse onion style, inside out. Let's do this. So z goes from 0 to 9 minus r squared. 0 to 9 minus r squared. Next, r goes from 0 to 3. And then on the very outside, we've got the theta goes from 0 to pi. That seems nice. So from 0 to pi. So inside here, we've got the square root of r squared, but r is non-negative. So that's exactly just r. And then our volume element, remember, is r. And then in order, dz, dr, d theta. So that seems very nice. So that means solving this, which would have been an absolute nightmare, can be done by solving this. Nice change of variables. Okay, so let's see here. So this is really just r squared, right? So maybe I'll take care of that. And then also another thing I want to notice is if I look here on the inside, there's absolutely no mention of theta. So theta is actually constant in respect to both z and r. And we know with integrals, we can factor constants out in front. So I'm going to factor the d theta here and then ultimately here. So yeah, since theta is constant, right, because there's no mention of theta at all here. So since theta is constant in respect to z and r, again, I'm going to factor that out in front here. So that seems nice. And then I've got the following. And so there's r squared, dz, dr. Now notice that the z integral, it does have r dependence. That means that there's r stuff either in the bounds or inside the function. So really, it's the bounds that are the issue. This would be constant otherwise. But so since the z integral has r dependence, I'm not going to factor this through. So I call this solving this reverse onion style inside out. So we're going to do the inside integral first and then the outside integral. This we know is just pi, right? So from Calc 1, we know the integral from a to b of 1 d theta is b minus a. So that's just pi. Okay, so we've got the integral from 0 to 3. Now for our z integral, this becomes, so the antiderivative of r squared, well, that's a constant. So that's going to be r squared times z. And then we're evaluating this specifically from z equals 0 to z equals 9 minus r squared, and then dr. So yeah, I just integrated this inside with respect to z. So if I carry through with the fundamental theorem of calculus, so I plug this in for z, but I notice this will vanish at 0, so I only get a contribution here, so I'm only going to plug this in. Again, so this minus 0 is not so necessary. And essentially what I'm left with is a Calc 1 style integral. Okay, so yeah, this goes in for z. Okay, so that seems pretty nice. Let's go ahead and distribute the r squared. So I've got pi, so this is the integral from 0 to 3. We've got 9r squared minus r to the 4th power when we add exponents, dr. So this we can just take care of via the power rule, so that seems pretty nice. And so by the power rule, we get the following. So this will be 9r cubed over 3. So that's going to be 3r cubed minus r to the 5th over 5, again by the power rule, from r equals 0 to r equals 3, but I only get a contribution at 3. I'm going to solve this in a sort of a specific way. So what I notice is that if I plug in 3 here, that's going to give me 3 to the 4th, right? Because 3 times 3 cubed. I'm going to write it like that. And that'll be 3 to the 5th over 5 minus 0. But notice this allows me to factor. So I can actually factor out a 3 to the 4th. And if I factor out a 3 to the 4th, I'm left with the following. So I've got 1 minus, looks like 3/5. But 1 minus 3/5 is just 2/5. So what do I have? Well, 3 to the 4th, let's note this. So note, 3 to the 4th is the same thing as 9 squared. So that's 81. So that's 81 times 2, which is 162 pi over 5.